In the modern world, we humans are completely surrounded by electromagnetic radiation. Have you ever thought of the physics behind these traveling electromagnetic waves? The great scientist Heinrich Hertz was the first man to transmit and detect electromagnetic waves. In his famous experiment, a high-voltage current was applied to the two ends of two metal wires, which generated a spark in the gap between them. This spark resulted in the radiation of electromagnetic waves. Those electromagnetic waves traveled through the air and created a spark in a metal coil located over a meter away. If you had placed an LED in that gap, the bulb would have glowed. This was a clear case of electromagnetic wave propagation and detection. However, before Hertz, the brilliant mathematician James Clerk Maxwell had already laid out the foundations for electromagnetic radiation by formulating 4 mathematical equations. However, these equations and the Hertz experiment raised a question: how do electromagnetic fields detach themselves from wires and propagate through a space? More specifically, what we need is a traveling electromagnetic wave and not a fluctuating one. Let's explore this logically. Consider an electric charge, which is moving at a constant speed. The electric field around it is shown. Now, imagine for a fraction of a second it accelerates. After that, it continues its uniform motion at a higher speed. What we need to understand is the effect of this acceleration on the electric field. The interesting thing is that the information does not travel at an infinite speed. Instead, it travels at the speed of light. Similarly, the information about the sudden variation of velocity of the charge does not get conveyed to the whole electric field region. The field near it knows about it, but the field far away still has no idea that the charge has accelerated and it is still in the old state. Let's separate out these regions with the help of 2 circles. Since the electric field cannot break, the field between these distances must transition. This transition field is known as a kink. The kink moves or radiates outwards at the speed of light. To show the kink animation in a clear way, let's move the camera along with the charge. We can say here that the acceleration of the charge has caused an electromagnetic disturbance, or electromagnetic radiation. Based on this understanding, we will be able to understand the most important experiment in the field of antenna technology, the oscillating electric dipole. The interesting fact about this simple oscillating dipole is that it produces electromagnetic radiation in a perfectly sinusoidal manner. Let's see how it is achieved. Before getting into the electromagnetics, let's understand how velocity and acceleration vary in this simple case. It is clear that at both ends the velocities should be 0, and in the middle the velocity should be at the maximum. This means that this is a case of continuous acceleration and deceleration. The electric field pattern is drawn here when the chargers are far apart and when the velocity is 0. In order to have a better understanding, let's examine one of the electric field lines. Let's observe the electric field line at t by 8. You can see that the electric field line is deformed. The reason for this deformation is simple. This time period is the region with the highest acceleration. As we saw earlier, accelerating or decelerating charges cause kinks in the electric field. In short, the old electric field does not get adjusted to the new field very well. This deformation is continuous since there is continuous acceleration in the charge. When 2 charges meet at the central point, the deformed line also meets there. After that, it detaches and radiates. This radiation travels at the speed of light. If you plot an electric field intensity variation with respect to length, you can see that the radiation we have produced is perfectly sinusoidal in nature. Please note that this varying electric field will automatically generate a varying magnetic field perpendicular to it. Now, let's have a look at how this applies to an antenna. A time-varying voltage is applied to the metal wire as shown. Due to the effect of the voltage, the electrons will be displaced from right to left and create positive and negative charges. With a continuous variation of voltage, the positive and negative charges will shuttle back and forth in the wire. This simple arrangement is known as a dipole antenna. The dipole antenna produces the same radiation as we saw in the previous section. In this case, the antenna works as a transmitter. The frequency of the transmitted signal will be the same as the frequency of the applied voltage signal. The same antenna can act as a receiver if the operation of the antenna is reversed. When propagating electromagnetic waves strike the antenna, the oscillating fields of waves create positive and negative charges at the ends of the antenna. The varying charge accumulation means a varying voltage signal is produced at the center of the antenna. This voltage signal is the output when the antenna works as a receiver. We can note here that for perfect transmission or reception, the length of the antenna should be half of the wavelength. This is the first antenna design criterion for proper reception or transmission. The second most important design criterion is a term called impedance matching. Perfect impedance matching will make sure that the waves are radiated in the most efficient way. When an alternating current passes through a circuit, it faces opposition from the combined effects of resistance, inductance, and capacitance. This combined effect is known as impedance. According to the maximum power transfer theorem, to transfer the maximum amount of power, the load impedance should match with the source impedance. For further understanding, let's take an example of a circuit containing an alternator as a source and a motor, bulb, etc. as a load. In this setup, to achieve maximum power transfer from alternator to the load, the impedance of the load must match with the impedance of the alternator. A similar impedance balance is required in the case of an antenna system. Since an antenna works on high-frequency signals, the impedance of the transmission lines also becomes important. Hence, to achieve maximum power, the impedance of an antenna should match to the impedance of the source and transmission line as well. If the impedances do not match, some portion of the power would be reflected back to the source instead of radiating outwards from the antenna. A free space has an impedance value of 377 ohms. In a parabolic antenna, a waveguide is used as a transmission line, which has a different impedance value from the free space. That's why a feed horn is also included in a parabolic antenna. This way, the impedance of the waveguide is matched with the impedance of the free space so that the EM waves can be received properly. We hope the concept of such an important engineering phenomenon is clear for you from this video. And please, don't forget to support us. Thank you.